Hey guys, um, this video is just a few hints for assignment 3 for Math 3272. So question 1, you have to compute the commutator subgroup of D4, D5, and Q, where Q is the quaternions. Let me remind you what those are. D4 is a subgroup generated by A and B, subject to these relations. Well, a to the fourth is b squared is the identity, and BA is a cubed b. D5 is the same, except I changed the 4 and the 3 to a 5 and a 4. Okay. A to the fifth is b squared is the identity, and BA equals a cube, a to the fourth b. Okay, and then the quaternions. There's you can use your favorite way to present this group. One way is it's the group generated by I and j, satisfying I to the fourth is j to the fourth equals the identity. Let's see. And then you can, I'll just write down as many rules as I know. I squared equals j squared equals -1. Things like that. Let's see, what else? Ij is -ji. That's enough. Okay, just use whatever you know about the quaternions. Okay, anyways. So you have to compute the commutator subgroup of each one. So notice that when I take the commutator of A with itself or B with itself, I just get the identity, because like, for example, like A commutes with A, just like that just says A times A equals A times A. So like, well, this is not the solution, but this is the start of the solution. Compute the commutator of A and B. That's AB, A inverse, B inverse. Then just use the rules of the group you're in. So this is in D4. In D5, they'll be slightly different, So A inverse is A cubed, B inverse is just B. That's because A inverse is A cubed because A to the fourth is the identity. So multiply both sides by A inverse, you get A inverse equals A cubed. And similarly for B inverse equals B. Right? Now BA cubed is just AB. So you get A squared, B squared is the identity, so you get A squared. Okay. Okay, so A squared is a commutator. Okay. And now, let H be the subgroup generated by A squared, which is just the subgroup containing the identity in A squared. Then look at D4 mod H. D4 mod H is a group where A squared is the identity and B squared is the identity, and BA equals AB. Because I take all these relations, well, I add in the relation A squared is the identity because A squared is in H, and I'm taking the quotient by H. Okay. And once I once a squared is the identity, you know, instead of ba equals a cubed b, well, a cubed is just a, so you get ba equals ab. In other words, this is an abelian group with 4 elements. Okay, I guess we should say how is H a normal subgroup. Well, if you conjugate by B, you see that you see like H is actually contained in the center of D4, so H is normal. So this is just like a routine check. Okay, so it's normal, so you can take the quotient. The quotient is abelian, and therefore, since this quotient is abelian, that implies that the commutator, oops, not G prime, the commutator of D4 is contained in H. Okay, if the quotient is abelian, that means the commutator has to be contained in this quotient, like this, the one that you quotient by. Okay. And now a squared was a commutator, so H is contained in the commutator subgroup, and this shows that the commutator subgroup is contained in H. So therefore, H equals the commutator subgroup. Okay. And so that kind of suggests the strategy that you should compute a few commutators to try and guess what the commutator subgroup is. Check that the thing you get is a normal subgroup. Check that the thing you get, you know, the quotient of that is an abelian group in the entire group, and then you should be good. Okay, so like we could try and guess what the commutator subgroup of D5 would be. We can compute in D5. We should compute the commutator of A and B. Right, so BA inverse is just AB. So you get A squared. So the commutator subgroup contains the subgroup generated by A squared. So you have identity A squared, A to the 4th, A to the 6th, A to the 8th, A to the 10th. A to the 10th is the identity because A to the 5th is the identity. Since A to the 5th is the identity, this is A cubed. So you just get the subgroup generated by A. Okay, so then our claim would be D5 prime is just the subgroup generated by A. Then you just have to check that, take this subgroup, the one generated by A, is it normal in D5, and is the quotient abelian? If yes, then this is the commutator subgroup. And then in Q, we just want like a prospective commutator subgroup of Q. So we compute the commutator of maybe like I and J, get IJ, I inverse, J inverse. So I inverse is actually negative I, J inverse is negative J. So in those minus, so you get IJ, and JI is negative IJ, so you get minus II, JJ. This is negative 1, this is negative 1, so you get negative 1. You get negative 1 times negative 1 times negative 1, which is negative 1. Okay, so we might guess that the commutator subgroup is, our guess would be that Q prime is the subgroup 1 and negative 1. Okay. And then you would have to verify that Q mod this subgroup is an abelian group. Okay, so that's just a few hints for question 1. You try it and see how it goes. I already gave some hints on Monday for question 4, but you know, it doesn't hurt to try and just give you a more, I guess, a path, right? The idea is to compute the center. So let G just be this matrix which is in the center of H. Then it commutes with every element of H. So let's just try a few matrices and see what happens. So like do H1 is going to be like this matrix. And then since G is in the center, G times H1 is H1G. So we compute GH1. And hopefully this gives equations on A, B, and C. Okay, so we compute. We get 1 plus A, 1, 0, and then we get B, C, 1. Is that right? Okay, so that's one thing we get. And then if we do H1G, what do we get? Maybe we get 1, 0, 0. We get A plus 1. We get 1 and 0, and then we get B plus C. We get C. We get 1. Okay, and then what does this tell us? It tells us that A plus 1 equals 1 plus A, that's fine. It tells us B equals B plus C, C equals C. And in particular, if B equals B plus C, then C equals 0. And then try the same thing with H2. And compare GH2 to H2G. That should give you an equation for A. And then what you should have are so in our matrix in the center, this has to be 0, and it turns out this has to be 0, so just verify that. And then prove like the resulting thing commutes with any matrix in H. So in the end, you have to show something like oops, this is not 0. That's O is a bad choice of letter. Let's say L. So just you have to show that your resulting matrix commutes with every other matrix. Okay, so you have to prove this equation. Okay, so this will tell you that every matrix like this is in the center. These kind of calculations tell you that everything in the center has, well, this one tells you that every matrix in the center has this entry equal to 0, and then working with this matrix tells you that every matrix in the center has this entry equal to 0, and then you continue from there. And the last question, question 5, well, you just have to compute a few things, you know. So, you know, all we have to do is just check. So, we define, so if we have sigma in S3 and we have a polynomial f with coefficients in x1, x2, x3, coefficients in the integers, and the variables are x1, x2, and x3. We have some polynomial. Then we define sigma f to be a new polynomial, and g of x1, x2, x3 is just f of x sigma 1, x sigma 2, x sigma 3. Okay. And now tau of g, if tau is another permutation, what is tau of g? Well, tau of g equals h if and only if h of x1, x2, x3 equals g of x tau 1, x tau 2, x tau 3. Okay, and then you compute what is g of x tau 1, x tau 2, x tau 3. Okay. Okay, so let's just try it on our example. You know, just to clarify things a little bit to see what happens. But sometimes you just have to see what happens. Okay, so our example was f equals x1, x2 plus x3. Now let's try sigma equals 1, 2, 3. Let's try tau equals 1, 2. This is, okay, so sigma of f is just f of x sigma 1, so sigma 1 is 2, and then sigma 2 is 3, so it's x3, and x sigma 3 is x1. Okay, now f of this is like x2 goes where x1 is, x3 goes where x2 is, x1 goes where x3 is, so that's sigma f. Okay, so this is our g. And what about tau of that? So tau g is just g of, well, tau switches 1 and 2, so it's g of x2, x1, x3. Okay, and so the x2 goes here. Oh, sorry. Yeah, the x2 goes there, and then x1 goes here, x3 goes there. Okay. So this is what should be tau sigma of f. If this were to be a group action, we need to show this, you know? So let's also compute what is tau sigma, and then use the rule to compute tau sigma of f, see if we get the same thing. If we don't get the same thing, well, we're done, because we only need to prove that it's not a group action, and that would show us it's not a group action. If it is a group action, then we have a good idea to try and prove it. Okay, so let's do it. Let's compute tau sigma and then do tau sigma of f, see what we get. So tau sigma, that's just 1, 2 followed by 1, 2, or sorry, 1, 2, 3 first and 1, 2. So 1 goes to 2, 2 goes to 1. Let's see, 2 goes to 3, 3 goes to 1, and 1 to 2. So it's just 2, 3. Okay, let's call this alpha, and now let's compute alpha f. That's just f of x1, x3, x2, and f is like first thing times second thing plus third thing. So you get first thing times second thing plus third thing. Okay, it's not a group action. Okay. Okay, so that would be it. Okay. Of course, you have to write it up nicely. So that's it for this, these quick hints. If you have any questions, just please send an email. Thank you.